The second law of thermodynamics was actually stated by two different people in different ways, and then later realized that mathematically they had said the same thing. The first one is the Clausius statement. It says, "There's no process is possible whose sole result is the transfer of heat from a body of lower temperature to a body of higher temperature." Okay, so spontaneously, heat never travels from low to high. The second one is the Kelvin statement, which says that no machine can be made that only absorbs energy by heat and then entirely transfers the energy out of the engine by an equal amount of work. Okay? And the key word here is machine. Okay? There are other processes that could do this. However, a machine is a cyclic process. Okay? And so therefore, there are some constraints on that. So, let's go ahead and look at the engine of a car. So we've got a piston here, and there's going to be some combustion in here, and this area is going to expand. Okay, so we're going to end up like this. Okay, so this has expanded, all right? And when it expanded, this went down, and it turns the little wheel, and it turns everything, and it's producing some energy. The problem is it's a cyclic process. If I want to do this again to get the wheel to turn a second time, I have to get back to here. And the only way to get back is to remove some heat. Okay? So we need to cool that area back down. Okay? And that's why your car has a coolant system. Okay? Another example would be a power plant. Okay? So here's a reservoir filled with water, okay? And we're going to take that water and we're going to boil it to make some steam, and the steam is going to go up, and the steam is going to turn some turbines, okay, big old fan-like things, and when those turbines spin, they're going to create some energy. Well, we're going to take this steam then, because we want to, the problem is we're going to run out of water. We need to refill that. So we're going to take this steam and we're going to have it in a pipe, and we're going to bring it down, and we're going to have to cool it. Okay? And the way that it's often cooled is by using a river. Okay? So maybe over at 3 Mile Island you've seen the big old towers. What's happening here is the cool river water is going into the tower and cooling off this steam so that it can go back and be in the process again. Okay? Again, a cyclic process, we have to remove some heat, okay? So, what this is saying is that basically our efficiency can never be 100%. Efficiency is going to be equal to the amount of work we get out, the net amount of work that we get out, over what we put in, okay? In this case, the heat that we are putting into the system. Now let's go ahead and look at the first law of thermodynamics, okay, which says that the total heat transferred is equal to the net amount of work plus the change in internal energy. We can solve for the net amount of work. Now what we know is that since the process is a machine and it is cyclic, okay, the change in internal energy is 0, okay, because it's cyclic again. So now we know that the net amount of work is equal to that, and we can substitute it in. So we can say the heat that enters minus the heat that's removed over the heat that's added. Okay, now we're going to go ahead and take it one step forward. We're going to simplify this. So we're going to say divide both the terms by the heat. Anything divided by itself is 1, so this is really 1 minus this. And that is equal to our efficiency. This is the equation that we will see used quite often. Now, we want a machine to be as efficient as possible. And the most efficient machine, theoretically, would be the Carnot machine. And there's a T on the end of it because it's French. Okay? And in this system, there are 2 adiabatic processes and 2 isothermal processes. And we end up that we could get So we have the efficiency is equal to 1 minus the temperature of the cold reservoir over the temperature of the hot reservoir, where this is like the river's temperature from our example, and this would be like the boiling water's temperature. And if we want this term to be really small so we can get close to 100% efficiency, then we need these to be as far apart as possible. The smallest, the coldest we can get, and then the highest or the hottest that we can get here to get the most efficient machine.